Welcome back for another edition of Sigma Notation. Hopefully you've had a day or two to practice some basic Sigma Notation skills, and we get to continue on today. You may have noticed on your homework there were a bunch of problems that I didn't really teach you how to do, where you were asked to rewrite a series using Sigma Notation. And so hopefully you were able to figure out a lot of those on your own, because I think they are kind of like fun puzzles that you can figure out on your own. But today we're going to give you some concrete strategies for how to do those types of problems. So we're going to finish up our notes today, and the first thing we're going to look at is rewriting series using Sigma Notation for arithmetic series. There are basically two types of series that you will encounter when we're working with Sigma Notation. And the first one is what's known as an arithmetic series. And all of these examples here are examples of arithmetic series, and if you notice for just a minute, I'll give you a few seconds to think about it, they all have something in common. And what you might have noticed after looking at a few of those, you probably needed more time, which I didn't give you, but they all kind of increase by the same amount. These just increase by 1, but these increase by 2, and this last one increases by 5 each time. But what they all have in common is that they're all increasing by the same amount each time. So that's what an arithmetic series is. It's a series that increases or decreases by the same amount each time. And the trick to these, I'm not going to give you a lot of structure on these, but the trick to these is noticing because they go up by the same amount each time, and you're repeatedly doing that, it's almost like you're repeatedly adding something. And what is repeated addition? Well, that's what multiplication actually is. Multiplication is defined as repeated addition. So what we're looking for is a constant, or the common difference becomes a constant multiple in all of these. So let's start with a couple basic ones, and then we'll get into the next two. So on the first example, 1, 2, 3, 4, 5, that's almost insultingly easy. That's like definition of a sigma notation problem. So we're trying to write in sigma notation. It looks like it starts at 1 and goes to 5, and we're just adding up whatever the number is, 1 plus 2 plus 3 plus 4 plus 5. I didn't even really need to think about whether that was an arithmetic series or not. It was so easy. And you'll see some of those on your homework that are hopefully just as easy. The next one I want to look at, I want to have a slightly different discussion about. And it is just increasing by 1, 6 plus 7 plus 8 plus 9 plus 10. So I know it's just going to be like plugging in a number, but I actually have a couple different ways that I could do this. I could start at 8, or why would I start at 8? I could start at 6 and go up to 10. That is technically correct. I add up 6, 7, 8, 9, and 10, plugging them all in. But normally, and you can think about this as an extra little challenge, normally we like to start our sums at either 1 or 0, and almost all the ones we will do start at 1. So how could I do the same series except start at 1 instead of 6? Well, how many terms are there? There are 1, 2, 3, 4, 5 terms. So I know I'm going to go from 1 to 5. And I know my constant multiple is just 1. It's increasing by 1 each time. So that's why it's kind of like 1n. But if I just did that, if I plug in 1, then I'll be starting at 1, not 6. So what's the trick here? How do I get this to adjust and go and start at 6 instead of 1, even though I'm starting at 1 as the index? Maybe even seems like a weird question. But the simple solution is if I plug in 1, I get 1. But I really want to start at 6, so I can add 5 more to it. And that actually works for each one. If I plug in 2, I'll do 2 plus 5, which is 7. If I plug in 3, then I'll do 3 plus 5, which is 8. And I get this same series using either one of these methods, but I would like to encourage you to try and do the more advanced one, which is always starting at n equals 1 or I equals 1. So we're going to try that same method on the next one. And hopefully you'll see some patterns starting to emerge. So we got 12, 14, 16, 18, 20. All right, so here's my thought process. I want to start at 1. I kind of said that on the previous problem. I can tell that there are 1, 2, 3, 4, 5 terms. So I know the series is I'm going to plug in 1 through 5 because that'll give me the 5 terms when I plug in each term. This time, it looks like it's increasing by 2 each time, by plus 2 each time, plus 2, plus 2, plus 2. And so that 2 becomes my constant multiple. The only thing left is to figure out that last little adjustment I made on the previous one. I added 5 to get it to be the right starting point. So if I plug in the first number, 1, 2 times 1 is 2. That is not the same as 12. I want this series to start at 12, not 2. So what do I add in for that last part to make this come out to be our first number? So I plug in 1, which is my first number I plug in. 2 times 1 is 2. Plus what equals 12? Well, 2 plus 10 is equal to 12. And so there is our solution. When I plug in 1, I get 12. When I plug in 2, I get 14. 2 times 2 is 4 plus 10, which is 14. When I plug in 3, I get 16. When I plug in 4, I get 18. When I plug in 5, I get 20. So that is the solution. And it might have been, again, a little easier if we had changed these numbers around a little bit, but I would like to challenge you to try and stick with the number 1 on the bottom so that you're always starting at 1. Let's see if we can do this last one a little bit quicker now that we know a little bit more about how these problems work. I'm going to start at 1. I count 1, 2, 3, 4, 5, 6 terms. And I notice they're increasing by 5 each time. So my constant multiple will be 5, 5n, and then I just need to figure out what to add or subtract at the end here to make it work out. I want to get 25 with my first term. When I plug in 1, I get 5 times 1, which is 5. So I need 20 more to get the starting number of 25. And that is a brief overview of an arithmetic series, which is one type of series. There are lots of types of series, but we're only going to look at one other type of series today, and that is a geometric series. Make sure that's centered. And just like the arithmetic series, these tend to follow a specific pattern when we look at these examples I've written up there. And you might look at the first one, you're like, oh, you're going up by 2, and then it's going up by 4. Oh, now it's going up by 8. So it's no longer going up by the same amount. It's no longer the same amount being added, but what each of these examples has is it's going up by the same multiple, which is what makes it, by definition, a geometric series. So instead of thinking about adding to get each term, we can think about multiplying. I can do 2 times 2 to get 4, and then I do 4 times 2 to get 8. And then times 2 to get 16, and times 2 to get 32. So it's the same process each time. It's multiplying by 2. And it might be fun to make you guys figure these out on your own, but for this one, it's almost like we can use this magic formula that I've written on the left side of your notes. So they all kind of follow this same template. So I'm just going to start applying that template to the first example and talk through it. So I'm trying to write it in sigma notation. I'm going to start at 1. And on the top here it says the number of terms. It was just like the arithmetic series actually in that way. 1, 2, 3, 4, 5. There are 5 terms, so I'm going to go from 1 to 5 on this example. And the next thing in my little template here is I have this number here, k, and that represents the starting value of the series. So the first value is 2, so I'm just going to copy that number down. The next one is the m. That's the constant multiple. And instead of, again, being increased by adding 2, this one is a constant multiple of 2. So that's where the constant multiple goes. And to finish it off, we just write an n minus 1. So it is kind of like a magic formula in the end. But let's just kind of check to see that this works out so that we can convince ourselves. And if we did a bunch of these problems without this template, you would have eventually, hopefully, maybe gotten to a similar place where you realized that this kind of pattern always works out. So let's just plug in 1, because it's always good to check our answer at the end to see if we get the first term. So this number here is supposed to be like our starting value. So why do we plug in 1? Does this actually end up being 2 like we want it to? So if we plug in 1 for n, that should have been in black. If we plug in 1 for n, we get 1 minus 1, which is 0. 2 to the 0 power is 1, and then 2 times 1 is 2. So this actually does give us the first value. And does it continue to work? If we plug in 2, our next value, 2 minus 1 is 1. 2 to the first power is 2. 2 times 2 is 4. So that worked for that number too. And we can continue to plug in, and we'll continue to see that it works. The reason this works, similar to the arithmetic series, just to make a quick connection here, the arithmetic series is increasing by plus 2 each time, and that resulted in a constant multiple. And that's because repeated addition is the same as multiplying. When we repeatedly multiply, that's the same as an exponent. So it makes sense that something with a geometric series increasing by the same multiple would have an exponent in it. Let's try the other two together. Let's write out our sum here. Let's see. Following the template, I'm always going to go 1, and I count 1, 2, 3, 4, 5 terms again on this one. And we're really just looking for the starting value. The starting value is 1 here, so that's pretty easy. The constant multiple, it looks like 1 times what is negative 5? Well, 1 times negative 5. And that pattern continues, times negative 5 each time. Times negative 5 times negative 5. So negative 5 is our constant multiple. I'm messing up my colors. Negative 5. And we complete it with the n minus 1. And the reason it's n minus 1, we talked a little bit about it up there, is that's because we want the 1 to be our starting value. And if we do n minus 1, that makes 0 our starting exponent, which makes this term kind of irrelevant. So it gives us our starting number there. Let's do one more together. I'm going to hit the right colors on this one. We're going to go from 1, 2, 3, 4 terms in this series. Our starting value is 6. And this should probably be the first step of the problem, even though I'm doing it almost the last step, is to notice that I'm increasing by the same multiple each time. That's important before we just start trying to plug it into a template. Each time it's going up by a multiple of 2. 6 times 2 is 12, times 2 is 24, times 2 is 48. So that 2 there will be in that spot, raised to the exponent of n minus 1. And again, we can convince ourselves that that's true by plugging in 1, 2, 3, and 4 to see if we get those 4 numbers. You can try that on your own if you'd like. But that is where we are going to stop for the day, almost anyway. Those are arithmetic and geometric series, which are the 2 most common types of series that you will see. There are other types of series, and I might even throw some at you on your homework. Ones that don't increase by the same multiple each time. But you can try to figure those out just like you did last night, as if they were a puzzle. I do want to revisit one question that I asked in the previous video as we look at these other tips and tricks. I'm not actually going to write anything down here. This space is for you to write down anything you want as you notice. But one question that might have been bugging you is like, okay, so why do we even care about this notation if it doesn't really save us any time? And if we were to study this for a long time, we would study a lot of shortcuts for doing this notation, but I'm going to show you the shortest shortcut of all by revisiting this question. What happens when I add up the numbers from 1 to 100? And what I want to show you is kind of a cool thing we can do on our calculator, which is really just do it on our calculator. And where we're going to go is where most fun things are, on the math button. And I probably should have looked this up in advance to remember where it is. I think it's on this one. If we keep scrolling down, yes. So math, if you just keep scrolling down all the way to the number 0, we see this little summation and we see our little sigma. And hopefully if you have a somewhat modern calculator, you can see that this template has popped up. And what we can do is just fill in this template with our sigma notation. I like to use the letter X just because I don't have to type in anything else. I can just press the X button. But if we can rewrite this in sigma notation, in other words, from X equals 1 to 100, and the function for this one is just X. So calculators are really good at doing repeated calculations very quickly. And so your TI-84 has that ability built into it. And I know I could have told you that on the first video and you would have saved a lot of time on your homework, but I wanted to save you some time. And when you hit enter, sometimes it can take a long time to calculate. And you can see that it adds up to 50/50, just like we got on video 1. But we can do much longer calculations than that. And we can even go up to 1,000 or 100,000. And you can see it's actually taken the calculator quite a long time to think about the answer, and I hope I didn't overload it with that one. But it actually is going through and calculating every single one of those 10,000 entries. And maybe it will solve before this video is over, or maybe I'll get bored of waiting for it. And the answer is I'm going to get bored of waiting for my calculator. But know that your calculator can do things like that. On your homework tonight, I would still like you, oh there, I finally did it. I would still like you to show your work when it asks you to. It just depends on what the problem is asking. And I wish you all good luck. And we will start looking at a brand new thing next week.